Hello everybody, Mannix here. Got a little bit of an experimental video here for you. How much weight does skeletonizing steel liners really shave off of a knife? Is it just a gimmick? Is it just a fad? Or is there actually something pretty considerable about doing it? Well, I can't exactly physically mill or drill out the liners right here on our experimental knife, but we can solve this issue more or less with math. And I think we're going to get a pretty accurate result right here. So first we're going to take apart this Milwaukee knife just so we can see and weigh the steel liners in here. As you can see, they are not skeletonized. So let's get a closer look. I'm going to just take this guy apart right here. Right tidy, all the screws are out. I'm just going to leave that in. Looks like that's our plunge. Really bizarre mechanism. It deploys with the button, but you cannot close it with the button. You close it with the liner lock. So strange. Wonder why this design never caught on. If they just made this a regular button lock knife, I would have been recommending it a lot more, but it's not. It's a weird ass liner slash, but I don't understand it. Here we have our two steel liners, and these are not flush mounted, as you could tell. Now, this isn't the right part, but it just sits parallel next to the handle. So first thing we're going to do to calculate this is simply weigh each liner. I'm curious to see what the difference in weight will be. So here are 0 ounces. 0.83 ounces. It's heavier than I thought it would be, actually, on that liner. And then the liner with our mechanisms here is 1.04 ounces. Damn. That's a lot heavier than I thought it would be. How is it that much heavier? Is it just this piece is making it weigh that much more? I don't know if I have a way to get it out. I didn't really try. I feel like it's kind of just stuck or glued or whatever process they put in there. It probably is just this little piece right here causing it to weigh that much more. That actually really surprises me. But anyway, looks like they skeletonized it a little bit. There's one hole right there. No, it's just to expose the button right there. So before we get our little math equation going here, let's roughly measure the dimensions of this steel liner anyway. It's going to be about the same as the other. Let's say 4.75, it looks like. Get the width here. I'm going to call that an inch. I know the widest point right here is a little larger, but there's also cutouts in here, and I don't exactly have the tools to do an extremely exact measurement here, but more or less 1 by 4.75 inches, I'm going to call it. I'm going to say the same thing for this. Again, this piece right here really surprises me. Surprised it makes it weigh that much more. 0.84 ounces. So, roughly a 4.75 by 1 inch steel liner. I'm going to say it's the same for both the steel liners as it would be with most other knives. And then we have 0.84 ounces per liner, let's just say. I know it's kind of a weird knife, but most knives it's going to be somewhere about the same. All right, so now let's drill some holes into this bad boy. I went with a drill bit here with a 0.5 inch diameter. I just used one of my spider codes to draw the circle in there. Calculated this earlier, but this can comfortably fit just about 8 of these holes, possibly one more. I'll show you right now how that looks. But we can fit just about 8.5 inch diameter holes into this liner. Now, I know I did measure this and it was roughly 4.75 inches by 1 inch, but upon further inspection, if we were to, let's say, melt all of this down and re-flatten it out, as in get rid of all the holes and cutouts that are already in here, we'd probably be left with, I want to say, a surface area of closer to just 4 inches, because we have a hole here. This could count as another hole if we put it next to that cutout right there. All of these drill holes, the lanyard hole. I'm gonna say, let's go down to 4 inches as our total surface area. Again, it's kind of a rough estimate, but it's certainly not 4.75 times 1. It's definitely less than that. We're being kind of conservative here, but let's just say surface area of 4 square inches. And of course, our circle right here, again, 1/2 inch in diameter. So how do we figure out the surface area of each hole with this theoretical circle right here? Very simple equation with a diameter of 0.5 inches that gives us a radius of 0.25 inches, and to find the surface area, that is pi times radius squared, and we get this big old number right here. But if we round it, just go 0.2, because I'm going to be annoyed typing all of this all the time. 0.2 square inches is roughly what each circular cutout is going to give us. So again, we have a 4 square inch surface area we're working with, and each hole we punch into this is 0.2 square inches shaved off of it. And again, we have 8. 0.2 times 8, 1.6. So that's just 4 minus 1.6. Again, the 4 square inches. So we're left with 2.4. So 2.4 in comparison to the original 4. That's 60%. So we got rid of 40% of additional material on this liner. So 60%, remember this was 0.84 ounces. So that 60% of 0.84 ounces is 0.504 ounces. So that's 3.36 ounces we have successfully removed from this one liner by punching in those 8.2 square inch holes. So if this liner looked exactly the same for the other liner, like if they were both symmetrical, obviously the other liner we have right here is not. There are more cutouts in here to accommodate this funky locking mechanism right here. But if this were like a lockback or something, we got rid of that, a triad lock or an axis lock or anything else pretty much, and the liner was more identical to that one, we could safely say we can simply subtract that same exact amount to the other liner if they were both skeletonized the same. And I don't see why they wouldn't be in that case. I mean, liner locks are a little different because they have to make a cutout in the liner, but for most other locking mechanisms, that's what we'd be left with. So we just multiply that by 2. So if we skeletonize both liners, that's 0.672 ounces we could shave off of the knife as a whole. Little over half an ounce. So that's actually more than I thought it would be. I was expecting it not even to be like 0.3 ounces at the very most for both liners, but one of the liners we can get about 0.35 ounces off of it by aggressively skeletonizing it. And then of course that doubles over to the other liner. So this tells us skeletonizing a knife of this length, anyway, kind of a medium-sized folder, we can get about half an ounce off of it. And again, that's being a little conservative. If you go really aggressive and really mill it with rectangular holes or something, you can go a little bit more than that. But I think it's safe to say skeletonizing a liner, going from completely unskeletonized to completely skeletonized with, you know, roughly a 4.75 inch length handle, you can safely get half an ounce off of it by skeletonizing it. Now, of course, if you have a really big knife with a 6-inch blade and a giant handle, that's even more weight you can take off of it. So it matters more the bigger and heavier the knife already is. So for smaller knives, it matters less and less. You can only take off so much weight off of a knife that's already very light and small. But that's actually pretty surprising. Here, I'm curious now. I wonder how much weight each hole took off based on our little virtual example right here. I just have to divide that by 16 because there's 8 holes in each liner. So each half-an-inch diameter hole, which is 0.2 square inches, that's how much surface area the circle would be taking, gets us almost 0.05 ounces off. So 2 holes would be like about 0.1 ounce. Again, we could go with like slightly bigger holes just so we have an even 0.05. So 2 holes theoretically would be 0.1 ounces, so 10% of an ounce for every 2 holes. I don't know, hell, let's throw in just 4 holes in here. If we don't want to really skeletonize it, then that's still about 0.2 ounces we take off. That's a total of 0.4 ounces we take off of the knife as a whole. So again, that kind of surprises me based on this little experiment we just did here. I didn't know it would take off that much weight. It didn't like really lower the weight that much, but it's a moderate. It is a considerable difference. So skeletonizing liners, what can we get out of this video? I'm going to say skeletonizing absolutely does make a difference in the weight, a noticeable difference. It's not a huge difference, but it's not so minor it's not even worth considering. It is a moderately considerable difference skeletonizing liners can potentially make when it comes to lightening up the overall weight of a knife. Pretty interesting. And again, this is kind of a rough estimate because this is not exactly 4.75 by 1 inches because we have a lot of holes in here, there's a lot of cutouts, and again, my estimate is about 4 times 1 inches. If we, again, were to melt this all down and shape it into a perfect rectangle to see how much material we really have, because it already is somewhat skeletonized, like all liners have to be to accommodate the knife and the locking mechanism. So very, very interesting results. The only next thing to do is to get the equipment to actually drill this thing and see if my theory was correct. But it's not really a theory, it's just math. The only part I did not have 100% information on was the exact specifications of the surface area of this steel liner right here. If I had that, we could basically guarantee an exact mathematical equation and understand the exact weight that would be shaved off. But I'm going to call this case closed. Yeah, lightening up a knife, it generally makes a difference. So next time you see a knife about this length, 4.75 inch handle, 3.5 inch blade, or whatever is medium length, if it's not skeletonized, you can probably safely say you can take about a half an ounce off if it was skeletonized, if it had steel liners in there in the first place. So that's it. Hope you enjoyed the video. Mannix out.